So this main learning target, which is called linear programming, is a technique we can use to find what we call the optimal solution to a problem or the best solution. So do you remember on our previous couple lessons when we do that shading with the inequalities and we get this feasible region? And remember how, like, for an answer, you can just pick any point inside of that shaded area. Like we did like the numbers of nickels, numbers of dimes, or whatever. So now we're just going to take it one step further, and we're going to say, out of all those possible solutions that make all those constraints true, what's the best combination of those two variables, of that x and that y? And that's what we mean when I say the optimal solution. We're trying to optimize our results, whether that's going to be maximizing our answer. So like different businesses, they often want to maximize their profit, right? What's the profit of a company? What does that word mean? Yeah, the money they make, right? And a job or a company, I mean, they're a company in order to make money, right? To make a living. And they often want to maximize their profits. So we can look at different constraints that a company has, such as what they have to buy, different costs that they have, the number of employees, all these things that cost money. But then when they're going to turn around and decide how much of something to sell or how much of some supplies to buy, and there's going to be a sweet spot where it's a nice balance between all these variables, all these constraints, and everything they need to money they need to put into the company versus what they're going to be selling, in order to figure out what's that best combination for us to make the most money, to maximize our profit. Other times you want to minimize things, like insurance companies want to minimize like the risk that they take whenever they have a enroll a new customer. And so sometimes we want to find the lowest number, the minimal. And so that's what this middle bullet point is saying. So we want to find the maximum or the minimum value of a particular function. Now, we're going to be maximizing or minimizing something different in every one of these scenarios. And so whatever we're trying to optimize, when I say optimize, that means either maximize or minimize. Okay, the optimal solution is the best solution, whether we want the biggest number or the lowest number. And so in our last lesson on Monday with these constraints, we're going to still be working with word problems, but there's going to be one new piece. That's all, just one new piece to this. And that's going to be something called this optimization function. And this is going to be another equation. So before, with the constraints, those are always inequalities. This is going to be one equation that also deals with our two variables. Remember how our first step was always to define x and define y, like your two different things you're trying to, you're coming up with those constraints for. So now we're going to have one equation with those same two things, and it's going to be a way to check to see what's the maximum value I can get out of those two or the minimal. And this is called the optimization function, or just a z function for short. And the reason we call it a z function is we usually write it as z equals and then some combination of the x and the y. All right, so that's kind of the general idea here. We're going to be going through some of these together in a class. That's what I've got in front of you. If you're at home right now, I had emailed all of you on Monday about picking up a packet. Unfortunately, only one of you stopped by to pick it up. So in order to grab these word problems that we're doing today, just go to my P-Learning calendar. It's the same way you get the notes, same way you see the videos. But if you go to Algebra 2, go to the calendar. And for today, you click on this linear programming, and you'll have a link down at the bottom, worksheet, and that's going to be the same packet that I just passed out to everyone here today. So make sure you grab a copy of that, or you load it up in a separate tab so you can read these word problems without of class time. All right, so let's keep looking in this linear programming. So the new thing, the new numbers we have, is we're going to have to now write one equation called this z function. Once we've got this z function, then the rest of the problem is going to be pretty much the same. We've got our constraints, right? We know how to identify those. We know how to graph them, and we do that little shading, right? And we get one feasible region, one shaded part of our graph that has all these X's and Y combinations, all these points that basically meet all those conditions in the constraints. So now the next thing is, out of all those points in the feasible region, we want to find the best combination of those variables. We want to find the best point, the one single X and Y that is optimal for our Z function. Basically, you're going to plug them into this Z function, this equation, and it's going to be a different number, and we're going to either pick the biggest number or the smallest number. Now, in that feasible region, we often have a bunch of points, don't we? Like in that shaded region, there's a whole bunch of different X's and Y's in there. Now, we're not going to test every single point. Instead, it turns out that for these Z functions, the best combination, the optimal solution, either the biggest number or the smallest number, is always going to come from one of the vertices of the feasible region. Now, a vertice, that's just the plural for a vertex. If you remember from geometry, I know that word is kind of scary around here, right? We don't like to talk about it. But a vertex is just a corner. So whenever you've got your feasible region, and maybe it's some weird shape like this, the vertices are just the corners. You just check, like in this case, there'd be 4 vertices. You just find those 4 coordinates, those 4 X and Y's, and you're just going to plug each one into this Z function, this Z equation, and get a number. Then you just compare those 4 numbers and just pick the biggest one if it's a maximizing, or you pick the smallest one if it's a minimizing word problem, which again, the word problem will tell you maximize or minimize. It says it right in there. So that's just what a vertex is. It's the corner or those intersection points of your feasible region, that super shaded area on our graph. All right, so now we're putting everything together. This is the complete process for linear programming right here. So you'll notice that part of these are still from Monday's lesson, right? We've got things such as number 1, defining your variables. We know how to do that. X is going to be bran muffins. Y is going to be corn muffins. You remember that problem, right? A new part here, write the optimization function, the Z function. This is going to be a new piece. Basically, it's going to be all the numbers in the problem that don't have to do with the constraint. It's whatever you're trying to optimize. Writing the constraints, those are just the inequalities. You've done that already. That was Monday's lesson. Graph the system of inequalities. Well, you've done that too in a way. This is just graphing a system of inequalities, doing the shading, and then finding that one feasible region. The new piece here, though, is after you graph them, we want to just identify the critical points. Plural. It's going to be more than one. So basically, once you have your shading, just write down the coordinates of all the corners, whether there's 3 corners or 10 corners. All right, just write those coordinates down, that X and Y combination. Once you've got those corners, then you just plug each one of those into this new Z function that we're going to write. And basically, this Z function is going to have an X and a Y in it, and you just plug those numbers for that coordinate into X and Y. And then after you've tried every one of those critical points, every one of those vertices, you just look at those numbers. Like if we're maximizing the profit of a company, you plug in the different numbers for X and Y, and you'll get different dollar amounts, $600, $800, $250. And if we're trying to maximize it, just pick the biggest number and say, oh, well, this coordinate, this X and this Y gave me the most money. So this is how many X's and how many Y's I'm going to make, right? I should make this many bran muffins and this many corn muffins to make the most money to help my business grow. Something like that. So there are a few. So again, this is a bit of a new step right here also. So 3 of these things you've done before, 3 of them are new, but they're easier, all right? The writing constraints is by far the most difficult part of this, right? Figuring out what that inequality should be. You're all great at graphing. You're really good at coloring things in and shading. I know that, right? We've mastered that a couple years ago, 2nd grade, 1st grade maybe. And then you just plot those points. And you take each point and you plug it in. And that's just basic calculation. And then you just pick the biggest one or the smallest number, whichever the question is asking for. All right, these steps are all listed on that worksheet that I passed out to you in class, or for those of you at home, it is on that that PDF worksheet that I showed you to get on the My P-Learning page. So you don't need to necessarily jot these all down. You've got them right in front of you. And we are just going to work through them all today as a group. Sound good? Yes, Mr. Wojcik. Awesome. Love the enthusiasm. This is special. Here we go. Suppose a lumber mill can turn out 600 units of product each week, different types of, I don't know, wood stuff. And to meet the needs of its regular customers, the mill must produce 150 units of lumber and 225 units of plywood. So those are different types of wood that you get from trees, I guess, the way you prep it or create it or something like that. If the profit for each unit of lumber is $30 and the profit for each unit of plywood is $45, then how many units of each type of wood product should this lumber mill produce in order to maximize their profit? Okay, so that's the whole scenario. Let's start by following those 6 steps. First off, just like we had on Monday with those constraints, what are our 2 variables? What is X going to be and what is Y going to be? What are the 2 different unknown quantities here? What would we say? Lumber and plywood, right? So he's got some lumber, he's got some plywood, right? They're the different types of things in this problem. That's going to be our X and Y. So step 1, X is going to equal, let's just call that lumber. And we'll say Y is going to represent the number of units of plywood. All right, step 1. Are we good with step 1, everybody? You can all do this, right? That's not bad. Same thing we did on Monday. Now, step 2, normally we would write the constraints, right? That's what we did on Monday. You start looking for these inequalities. But it's going to be easier if you write this new optimization function first, because whatever numbers we use in the z function, those numbers will not be part of the constraints. And a lot of times students get confused. Well, what is a constraint and what is part of like my optimization piece here? So step 2, I want you to look for the words maximize or minimize. Do you see that word somewhere? Maximize or minimize? Generally, it'll be in the last sentence. So right here, I see the word maximize. So that's telling me 2 things. 1, I'm going to try to look for the biggest number, right? I want to make the most money. I'm a company. I want to grow my business. But what am I trying to maximize? Well, it tells you right here. I'm trying to maximize profit. So that tells me that all the numbers that have to deal with profit are going to be in my z function and what I'm trying to maximize in this scenario. So to write the z function, we write z equals, and now I'm going to have 2 different terms, one with an x, one with a y, right? One for each of my variables, but they're going to have some number in front of them, and that number is going to be whatever has to deal with what I'm trying to maximize or minimize, which is profit in this case. So looking at that word problem, what's the profit that we get from lumber? $30. It says the profit for lumber is $30, right? So for every unit of lumber that we sell, we make $30. So I'm going to write that as 30x, because x is the number of units of lumber. So if I sold 3 units of lumber, my profit would be 30 times 3. It'd be $90. You just multiply them together, right? $30 for every x, $30 for every unit of lumber. But that's not the only way I make a profit. I also make a profit from the plywood I sell, right? What's the profit on plywood? Yeah, right there. It says the profit for each plywood is $45. So what should I write in my z function next to represent that profit? 45y, right? Because y is the number of units of plywood. 45y. y. So this right here is our optimization functions. That's the new piece right here. And basically, I can plug in different combinations of X and Y, different combinations of lumber and plywood, plug it into this function, add it up, and that's going to tell me how much money I'm going to make altogether, right, from selling my two types of product. So that's step 2, the Z function. All right, there's only going to be one of these, and you always look for that maximize or minimize word to figure it out. All right. What's next? What's step 3? Constraints. Oh, we're good at constraints. We've done that already in earlier lessons. Obviously, to make a lot of money, I could just sell like 2 billion units of plywood and 3 billion units of lumber, and I'd make a boatload of money, right? That'd be awesome. But there are some costs to do with that, right? I'm limited with my resources and things like that. So what are some constraints? Basically, look for the other numbers in the problem. Now, any number that we've already used, like the 30, the 45, it helps me to cross those off so that I don't accidentally use those again when writing my constraints, because each number is only going to be used basically, one time. If it's for the optimization, then it's not going to be used in a constraint. All right, so what's one constraint that you see up here? What's one thing that limits us? Okay, that first sentence says that they can turn out 600 units of product. Now, that's not lumber or plywood specifically. That just says altogether, we can only produce 600 things, whether it's X or Y, whether it's lumber or plywood. So one constraint will be if I just add up X plus Y, if I add up all the lumber I make and I add up all the plywood I make, I'm going to compare that to this 600 total units of product, and what inequality symbol should go in between those two. Yeah, I can make 600. Am I able to make 700? No, we couldn't go over that. Could I do less than that? Would that be okay? Yeah. So this X plus Y could be less than 600. Could it be equal to 600 exactly? That's allowed, right? If I can make 600 units of product. So that's one constraint right there. X plus Y, all the plywood and lumber that I make in a week, it's got to stay under 600 or equal to 600. I can't go over that. I just don't have the resources or the time, or my mill just will break if that happens. All right, so that's 600 units of product. Are there any other constraints in this problem? Basically any other numbers we see? Yeah, it says that it must produce 150 units of lumber. So that's X. So basically it's saying X has to be at least 150. So could it be more than 150? Would that be okay? Yeah, I could go over that number. I couldn't go under. So my next constraint is going to be X, which is the lumber. It's got to be 150. So I'm going to write it's got to be greater than or equal to 150, right? I've got to have at least 150. Units of lumber. And also in that sense, it says that we know we're also going to need to produce 225 units of plywood. So what would that inequality look like? What would that constraint be? Awesome. So plywood is Y, and we need to have at least 225. So I'm just going to write Y has to be greater than or equal to 225. So those are our 3 constraints. Is there anything else that we might be missing? Let's see, we got the 150, the 225. Doesn't look like there are any other numbers in the problem. Doesn't seem to be any other constraints that we have. The only other thing that you just want to keep in your mind would be, if you remember on Monday, I talked about those 0 constraints, those floor constraints. Basically, like the smallest number of lumber I could produce would be 0, right? I couldn't make negative. So when we go to our graph, we're just going to be in quadrant 1, positive X, positive Y. Just to remind you, we're not going to be making negative plywood. That just would be insane. It'd be like in a black hole or something. So those are the first 3 steps for the word problem. And step 4 says to graph. All right, we can graph. We're good at graphing. And do we graph the z function, the optimization function, or do we just graph the constraints? Just the constraints, right? That's an important piece to realize. We're only graphing those inequalities. That z function is going to come into play later when I test out those different critical points of my feasible region. So for right now, I want to graph those 3 constraints. Now, in order to graph them, we would want them to be written in slope-intercept form. So that first inequality, I'm going to rewrite it in slope-intercept form just by subtracting an x from both sides. So this will be y is less than or equal to 600 minus x. Then I'm going to graph the x greater than 150, y greater than or equal to 225. So we've got 3 constraints to graph. So to graph this first inequality, I've got a y-intercept of 600. So should I count up 600 lines on my graph? No, that's not going to work, right? That's way too big. Instead, what if we, so we need to scale our axes. Maybe we can just go by 100, right? Let each line represent 100 units. That'll be enough to graph all these, wouldn't it? It'd be pretty good. So I'm just going to go ahead and write, all right, this is 100, and then 200, 300, 400, 500, 600, 700. We probably won't need to go that high because it looks like my biggest number is 600, but it would still go to the top. And then remember, whatever you scale your y-axis with, make sure you scale your x-axis the same way. And so it's 100. This would be 200, 300, 400, 500, 600, 700, 800. That's an 8. Trust me. I just wrote every other one on the bottom, just otherwise the numbers would all blend together. I don't have enough room. So we've got our axes all set, scaled properly. We can go ahead and graph these lines. First up, I've got 600 minus x. So we start by putting a point at 600 on the y-axis. And what's the slope of that inequality, that negative x? Negative 1 over 1. So for my slope, I'm going to go down 1, right 1, down 1, right 1. And so down 1, right 1, put a dot right here, there. Just going to be a nice diagonal slope. It's a less than or equal to, so I'm going to draw a solid line through those points. And then would I shade above this line or below this line? What do you think? Above or below? So we look at the symbol right here. That's a less than symbol. It kind of looks like a diagonal L. So you'd shade below it, right? So and remember, for these inequalities, since we have a bunch of them, instead of doing like super shading, I'd recommend just drawing like little arrows, a couple of them, just to remind you, hey, I will be shading my feasible region, but I want to wait until I've got all my lines drawn so that I don't have like tons of pencil or pen or whatever all over my paper. That'll easily be able to identify that feasible region. All right, let's graph these next 2. So this one right here, it says x is greater than or equal to 150. So that's an x. I'm going to look on my horizontal x-axis. I go to 150. Well, if this is 100 and this is 200, then 150 should be right in the middle. And then for any x line, it's always going to be a vertical line. So I'm going to draw a vertical line straight through that point. And then for any x line, it's always going to be a vertical line straight through that point. And then for any x line, it's always going to be a vertical line straight through that point. And then for any x line, it's always going to be a vertical line straight through that point. And then for any x line, it's always going to be a vertical line straight through that point. And then for any x line, it's always going to be a vertical line straight through that point. And then for any x line, it's always going to be a vertical line straight through that point. And then for any x line, it's always going to be a vertical line straight through that point. And then for any x line, it's always going to be a vertical line straight through that point. And then for any x line, it's always going to be a vertical line straight through that point. And then for any x line, it's always going to be a vertical line straight through that point. And then for any x line, it's always going to be a vertical line straight through that point. And then for any x line, and it's a solid line. Straight up and down through x equal to 150, because every point on that line has an x coordinate of 150. Now, shading for this one's a little different because I always have you thinking above and below, up and down. But because it's an x, there is no up and down. There's only a left and right. But if you look at this inequality symbol, it says x is all the numbers that are greater than 150. So where is x bigger than 150? Would that be to the right or to the left? To the right. Those are the bigger numbers, right? 150, 200, 300, 400. So I'm going to draw little arrows kind of pointing to the right. Remind me, I'm going to shade to the right of that line. We have one more constraint to graph. I'm going to make this purple. Y is greater than or equal to 225. So this is going to be a horizontal line because there's only a y variable. I go to 225 on the y-axis. Now, this is 200, and that line there's 300. The middle would be 250. So like 225 would be like 1/4 of the way between 200 and 300. Just get it somewhat close. Then we draw a horizontal line. It's solid because it's that or equal to piece. And now shading, do I shade above this line or below this line? So look at that inequality, that's a greater than. Greater means up, above, higher than. So I am going to shade above this line. So we can draw little arrows going up, up, up. So now, do you see where the feasible region would be? That one little like mini triangle in the middle has arrows pointing into it from every one of those lines. So go ahead and shade this portion and right there. Here, I'll highlight that so you can see a little bit better. So that little triangle there, go ahead and you can shade that part in. That is our feasible region. And that's what we've been doing the last couple lessons, right? Graphing inequalities, doing the shading. Now that's part of step 4 is graphing and identifying this feasible region. But the next part is we need to identify the vertices, all the corners of it. So how many points are we going to look at here? How many corners are in that shape? There's 3 of them, yeah. We need to just identify those 3 coordinates. And so there's going to be 1, right? I don't want to use yellow, I use green. So there's 1 corner, there's 2 corners, and there's 3 corners. So I need those 3 intersection points, and we're going to write those ordered pairs out x and y. Now on these graphs, it's not a precise, value. I can't see exactly what point that is, what number that is. But if we remember what we are graphing, like if I look at this point down in the lower left, I know that that x coordinate was this number right here, which what is that number? Do you remember? 150. Yeah, so I know one point is at 150. And its y coordinate, well, that was over here, like 1/4 of the way from 200 to 300. So that one was 225 when we graphed that horizontal line. So I know that that's going to be the y coordinate, 225. So that's 1 point. Above it, we've got another intersection point. And I know what my x coordinate is. So I know the x coordinate is that same 150. But do we know exactly what that y coordinate is? It's between 400 and 500, but do we know exactly what that value is going to be? We don't. Bummer. So how do we do this? How do I find the intersection point of two lines? Is there some method we have where I could substitute something in or eliminate something or Kramer rule something? What am I talking about? Solving systems of equations. Remember, if you've got two equations, we can find their intersection point by using like the substitution method or elimination, right? You're going to be tested on this next week. So what we need to do is find the intersection point of those two lines, all right? Now, that vertical line, that green one, this is actually going to be pretty easy though, because that green line had the equation x. And for this part, to find the intersection point, don't worry about the inequalities. We already have the shading. So we're just going to treat them like equations. So I'm going to use equal signs. So that line is x equals 150. That red diagonal line, that had the equation y equals 600 minus x. Now watch how easy this is going to be, everybody. I'm trying to find the intersection point of these two lines. Since one of them is just x equals 150, all we need to do is take this 150 and just plug it in right there for x. If we do that, what do we get for a y coordinate? Yeah, exactly. 600 minus 150. Whoops. Doesn't that just equal 450? So that's the y coordinate that goes with this x coordinate. So 150, comma 450. All right, so when it's a vertical line or horizontal line, it's very easy. You just plug that number in to whatever that like diagonal lines equation was. Very simple. So 150, comma 400 is our second critical point, our second vertex. We need that third one. And that third one is down here. And that's going to be the diagonal red line intersecting with that horizontal purple line. So we're going to do a system of equations again, right? And so let's think about what are those two equations? Well, we know what the diagonal line is. That was just y equals 600 minus x. And that horizontal purple line, well, if it's horizontal, that's a y equals, and that was just y equals 225. And so we're finding the intersection point of these two lines. And whenever you've got just a single number like this, right, y is the number 225, all we need to do is plug it in to that other equation and solve it for x pretty easily. So we're saying, all right, 225 equals 600 minus x. So to solve this for x, I can add x to one side and subtract 225 from both sides. So x is going to be 600 minus 225. Does anyone know what that equals? 375, yeah. So x equals 375. So this is our next coordinate. When x is 375, y is 225. That's going to be our third critical point, our third coordinate. So 375, comma 225. So make sure you keep the order straight. Make sure that x coordinate number is first and the y comes second. All right, so we've identified those three critical points. The 150, 225, 150, 450, and then 375, 225. So right now, we know that back to the word problem, we're trying to maximize our profits. And I want to know how much lumber and how much plywood should I sell to make the most money. And so I need to determine what combination of plywood and lumber should I sell. And I know that the best combination to make the most money is going to be from one of these three combinations right there. Remember, X is the lumber, the X coordinate is the number of lumber, the Y coordinate is the number of plywood that we should sell. And so we're going to now plug each one of these into that Z function to see, okay, well, how much money do I make by selling this much lumber and plywood? How much money do I make selling that much lumber and plywood? And we're just going to compare those three different numbers and say, oh, I want to make the most money. I'm going to pick that biggest number. And that's going to tell you, oh, that's how much I should make. All right, so you have one more small step. So we're going to take our Z function in green. That's that Z equals 30X plus 45Y. So let me rewrite that. Z equals 30X plus 45Y. And all we're doing, everyone, is plugging these numbers in to that Z, those different coordinates into that Z function for X and Y. So if you have a calculator, now would be a great time to grab that out. That'd be very easy to do. We're just plugging these in for each possibility. Oop. So with the first scenario, 152.25. Let's see how much money that makes us. So I plug these in. I've got 30 times X, which is 150, plus 45 times 225. And what does that equal? All right, everyone, calculators out. Because you're going to be doing this on your own. So, I mean, you can multiply those by hand for sure, but it's just going to be a lot easier. So 30 times 150 plus 45 times 225. And then we get an answer. I got a 14,000 something. Oh, that's tricky. Anyone else get 14? Yeah, that's what I got. So with this first combination, we got 14,625. Remember, that's dollars. Is that a good amount of money? 14,000 bucks? I'd take that. That's in a week, right? Whew. But this specifically was already said to be profit. It's pure money in your pocket. I'm going to go into the lumber business. See ya. I'm pretty sure these numbers are all just made up. Don't quit school to become a lumberjack or lumberjill. All right, second combination. So I'm going to check this second coordinate, the 150, 450. So take your calculators. We're going to do 30 times 150 plus 45 times 450. What'd you get? Gavin, you did it in your head again?
Yep, I learned 26 last time.
Awesome.
I know how to add them.
Adding is super important in Algebra 2. All right, what's the answer?
Not the equation. No, I figured out how to add.
Oh, good. That's an improvement. Awesome. What'd you get, Vegas?
24,750.
That's what I got too. Anyone else? 24,750? Fantastic. Oops, let me get a pen. 24,750, and that's dollars. Okay, that's a little bit better, isn't it? That might be our best bet, but we still have to check that last possible combination just in case. 30 times, in this case, my x coordinate is 375 plus 45 times 225. So we type that in, and Mia, what'd you get? Me too. All right, so we got $21,375. All right, we're done with all our calculations at this point, and now we just have to select the correct answer. This word problem says that we want to maximize our profit. Look at these three different dollar amounts. What's the biggest number, everybody? Yeah, right here. So that's the most money. So now we look at the X and Y. 150, 450. That is the optimal combination of lumber and plywood that we should produce for our company in order to make the most money. So that's what I'm going to do. Every week, I'm going to focus on making 150 units of lumber. Then I'm going to make 450 units of plywood. And so step 6 is just writing that out as a single sentence with words. So don't just box up 150, 450, because like imagine if a company came to you as a brilliant mathematician like you are and said, hey, math person, can you tell me how much lumber and plywood I should make in order to maximize my profit? And you do all this work and you give them a sheet of paper that says 150, 450. Here you go. Like that's not going to mean anything to them, right? So instead, you want to write one sentence that just says, I'll type it so it's cleaner. So 150 was the number of units of lumber, right? X was lumber. And did this person have a name? No, it's just a lumber mill. Lumber mill should produce 150 units of lumber and 450 units of plywood. For a maximum profit of $24,750. You should, there, I'll make it nice and formal. So you should produce 150 units of lumber and 450 units of plywood to earn a maximum profit of $24,750. Whew. First off, can you see how this is actually useful math in the real world? For the first time, right? In all of high school, you're like, oh my gosh, it's useful math. I know, it's crazy. Second, was this a lot of steps? Was this a lot of work? Yeah, look what time it is. It's been like 45 minutes and we did one problem. It's a lot of steps, but were any of these steps really difficult by themselves? Like plugging in numbers for X and Y, is that difficult to do? No, you can all do that, right? Graphing lines, is graphing a line difficult? Not really. You've got that down. If you think about each one of these steps on their own, they're pretty simple. This problem is just a long problem, but I don't want you to get confused and thinking it's a difficult problem, right? Difficulty means like you won't be able to ever do it. But this is just a longer problem. You can do it because they're smaller steps, they're easy steps, and you can do this process. But obviously, we need to practice, right? So First off, are there any questions on any of these steps that we just did together? Or anything that you're so confused on, you want me to go over again? I'm going to do another example with you, but just right now, I want to make sure, how are we feeling about this? Thumbs up or thumbs down? Did you follow, like, okay, I think I can do this with some practice. I can get this process down. Okay. Well, let's look at another one. Let me make this a little bigger first. So example number 2. Yep, let's turn the page right on the back. So the manager of a gift store is printing brochures and flyers in order to advertise different items that it's got for sale. And then she says that each brochure costs 8 cents to print and each flyer costs 4 cents to print. A brochure requires 3 pages, a flyer takes only 2 pages, and this manager doesn't want to use more than 600 pages total. They're trying to keep that number down. But she does need at least 50 brochures, and she needs at least 150 flyers. So how much of each should she print in order to minimize the cost? All right, there's like 20 numbers in that problem, right? How are we going to figure this out? Well, just follow the steps. Step 1, define your variables. What are the 2 unknowns in this problem, everybody? Brochures and flyers. So let's say X equals the number of brochures, and Y is going to represent the number of flyers. Those are clearly our 2 unknowns, right? We have both of them written together in almost every sentence. That last question word sentence is always a good place to look for your variables. How many of each? So it's asking you, how many of each of the 2 things? That's our unknown. I don't know how many X's and how many Y's. I don't know how many brochures and how many flyers. Step 2. Let's figure out what numbers have to deal with the optimization, because then I can get rid of those numbers when I'm writing my constraints, right? Find that Z function first. Z equals. Now, in order to figure this out, which numbers go with it, we need to look for that optimization word. Do you see the word maximize or minimize somewhere in this word problem? Usually it's in the last sentence. What are we trying to minimize in this case? The cost. It says right there. We want to minimize the cost. That tells me exactly what should be in my Z function. Okay, I'm trying to minimize cost. That means my Z function needs to pertain to cost. So look back in the word problem, and what's the cost of a brochure? All right, it says each brochure costs 8 cents. Perfect. And so I'm going to write 8x, 8 cents for every brochure. And I need to think about the cost of a flyer. What's the cost of a flyer? It's 4 cents. Right next to it, each flyer costs 4 cents. So 8x plus 4y, and that is our Z function. So we're now going to save that for the end, right? Once I find those critical points in the feasible region, we're going to plug them all into this Z function, okay? But for now, just box it up, cross off those numbers so that you don't use them again when we're writing our constraints, because you never know exactly how many constraints you're going to have in one of these problems, and you don't want to accidentally create a constraint dealing with what you're trying to optimize. So let's figure out, what are the constraints? Again, basically just look at the other numbers in the problem. Do you see any other constraints in there? So here's something, right? There's a number. It says a brochure takes 3 pages of paper, where a flyer takes 2 pages of paper. Am I limited by the numbers of sheets of paper I have? Yeah, how much paper do we have? 600. Doesn't want to use more than 600. I can't use more than 600. So that's going to be a constraint right there, right? The amount of paper that a brochure uses plus the amount of paper that a flyer uses can't be more than 600. So the brochure takes 3 pages. We'd write that as 3x. 3 pages for every brochure. 3 pages for every x. I'm going to add in the flyers. Well, each flyer takes 2 pages. So we'd write that as 2y. It's 2 pages for every flyer that I print. I'd add those together and I'd get the total number of pages that I'm using. And that number can't be more than 600. Could it be less than 600? Sure. So I'd say less than or equal to 600. So 3x plus 2y is less than or equal to 600. And then just to keep me sane, I'm going to cross off those numbers so I don't accidentally use them again. Do you see any other numbers somewhere in this word problem? I do too. She needs at least 50 brochures. Right? That right there is one constraint. I need at least 50 brochures. Brochures are X. And if it's going to be at least 50, would that be greater than or less than 50? A greater than. I can be over that number. I can't be under it because I need at least. Like 50's got to be the lowest number. So X has to be at least 50 or greater than or equal to 50. Cross that off. She also needs at least 150 flyers. What's that inequality going to look like? Okay, flyers are Y. It's got to be at least or greater than or equal to 150. I think that's it. What about you? Are there any other numbers in there? I think we got it. All right, after we have all these constraints, what do we do with them? We graph them. So let's graph these constraints. Now to graph them, we want them in slope-intercept form. Those bottom two are fine. That's just going to be a horizontal line and a vertical line. But that first inequality, 3x plus 2y, we do want to rewrite that in slope-intercept form. So let's get the y by itself. We'll subtract the 3x. That gives us 2y is less than or equal to 600 minus 3x. And then to get the y by itself, we'll just divide by 2. But you have to divide every term by 2. So y is less than or equal to 300 minus, now since 3 doesn't divide by 2 evenly, we just leave this as a fraction, 3 over 2x. And that is great because remember, that's the slope. Slope is rise over run. So I know I'm going to go down 3, right 2. Now we're going to graph this. Again, my numbers are 150, 300. I'm not going to go by ones, obviously. In this case, I could do hundreds again, but that's only going to get me up to 3 lines. So maybe I'll go by 50s in this case, just to give me a little more room. So I'm going to count 50, 100, 150, 200, just spread it out a little bit. So the first line's 50. The second line will be 100, 150, 200. I'm only writing every other one just to make it look cleaner so the numbers aren't all mushed together. 250, 300, 350, 400. And remember that there is no right or wrong way to do this. Yeah?
Since we have no more than 600 pages, does that not really matter?
So the only thing that's going to matter is the numbers in our equations that we're writing. So it was 600 initially, 600 pages, but because we divided by 2, that brought the number down to 300. So we don't need to go up to 600. No, that's a great question, sir. All right, 100, 150, 200. I'll go to 300 and 400. All right, that's going to be like here, here, there, and there. Then the lines in between are 50s. Okay, so we scaled our axes, and we want to graph each of these. Now that diagonal line right here, 300 minus 3 halves x. So we're going to start at 300, put a dot. The slope is minus 3 over 2. So from that point, we're going to go down 3 units and right 2 and put a dot. So count down 1, 2, 3 and right 2 units. And there's our next point. Make sure you go down 3, right 2. And we can do that again. Down 3, right 2. There's our next point. This is an or equals to, so it's going to be a solid line. And because it's a less than symbol, right? Y is less than or equal to this line. We're going to shade below. We're just draw little arrows pointing downwards. Down, down. Just to remind me that we'll shade below this line. All right, I'm going to graph this. X is greater than or equal to 50 in red. So that's an X. I go on the X axis to 50 and put a dot. That's right here. And we're going to draw a vertical line cutting right through that point. And it is a solid line because it's or equal to. So we're drawing this vertical line right through the part where X is 50. And it says X is greater than or equal to 50. So is that to the right or to the left of this line? To the right, greater than. Numbers bigger than 50 are to the right. So like that's where things are greater than. X is greater than 50. And this third line, Y is greater than or equal to 150. Okay, so that's going to be a horizontal line because it's a Y. I go to 150 on the Y axis, and I put a dot. And we draw a horizontal line through that point, all the way across. And are we going to shade above this line or below this line? Biggest says up. Anyone agree with him? Greater than means above, right? So we shade above this line. Above, above, above. And you see there's a very tiny region of our triangle right in the middle that's going to have the shading from all 3 of these. There, there, there. All right, so we've got our feasible region. Do I need every point in that feasible region or just a few specific points? Yeah, those few specific points, we call them the critical points. The word critical just means important, the ones we're looking at. And in this case, it's going to be all the vertices, all those corners. So we need that point there for 1. So we need to find that coordinate. Now we know what the x coordinate is because that's on that x equals 50 line. So I know 1 is going to be x is going to be 50 comma something. Now to get the y coordinate, well, I need to solve this system of equations. Essentially, I'm going to plug this x value into that diagonal line. So let's do that. So we know x equals 50. That's the vertical line. And I need to find this diagonal line. The equation of that diagonal line was y equals 300 minus 3 over 2x. So we're solving this system of equations. And again, it's super easy when it's just an x equals or a y equals, because all you do is plug that number into that second equation and you're going to get your y. So just take this 50 and plug it in right there for x. So 300 minus 3 over 2 times 50. Now a fraction times an integer, remember, just take the numerator, the 3, multiply that by 50. What is 3 times 50? We got this. 150. Now divide that by 2. What's 150 divided by 2? 75. So this is 300 minus 75. What's that going to give us? 225. Can't add, but you can subtract, Gavin. So that's the y coordinate. 225. All right, so that's one critical point. Let's find the next one. So down here in the bottom left corner, that one's easy. I don't need to do any calculations because it's just on the line x equals 50. So I know the x coordinate is 50. And that horizontal line is the equation y equals 150. So I know the y coordinate is 150. Yeah. Oh, like the order that I write them in? Nope, not at all. Because Carson, we're going to be just plugging each one of these into that z function, and then we just pick like the biggest number or the smallest number. So it doesn't matter like which way I go around my my feasible region. Good question. But yeah, you can find them in any order. And then we've got this bottom right corner. We need to figure out that coordinate also. And so the equations of those two lines, we need to find their intersection point. So let's write those equations out. We've got y equals 150 is that horizontal line. That diagonal line is y equals 300 minus 3 over 2x. So we're trying to find the intersection point of these two lines. We could just plug this 150 in for y. Make sure you don't plug it in for x, right? This doesn't say x is 150. It says y is 150. So 150 equals 300 minus 3 halves x. We need to solve this equation for x. Let's start by subtracting the 300 from both sides. So that's going to give us negative 150 equals negative 3 halves x. Oh, those darn fractions again. First off, if you have only two terms and they're both negative, you can divide both of them by a negative 1. And that's going to make them both positive. Right? I divide one side by a negative 1, I divide the other side by a negative 1. It just flips the signs just to make it easier. So just get rid of those negative signs. And now I've got to cancel out a fraction in front of a variable. And again, we're going to see this throughout the year. We had this in an earlier unit. But to cancel out a fraction, you just multiply by its reciprocal. So that fraction is 3 over 2. Its reciprocal is 2 over 3. So we multiply by 2 over 3. on both sides, times 2 over 3. 2's cancel, 3's cancel. And then on the left, we have 2/3. Looks really messy, hang on. 2/3 times 150. And this is actually a pretty nice calculation, because what is 2 times 150? And what's 300 divided by 3? It's 100. So then we get 100 for x. And that's going to be for our third critical point. So when x is 100, that y coordinate was 150. Okay, so those are our 3 critical points of this feasible region. We're just going to go ahead and plug each one of those in to that z function from the second step. Let me clean some of this up for us. And let's see, where's our z function? Oh, that's in red, the 8x plus 4y. So z equals 8x plus 4y. So grab your calculators again at this point. This is the fun part, nice and easy. You're just going to plug each combination of x's and y's into this z function. So I'm going to take 8 times my first x coordinate, which is 50. I'm going to add 4 times, let me change that, plus 4 times my y coordinate for that first point, which was 225. So go ahead, take your calculators, type these in. 8 times 50 plus 4 times 225. And then we get a number? You do that in your head?
Yeah.
You rock star.
Finally did it.
I'm so proud of you. You have no idea, Gavin. That is remarkable. 1,300. Anyone else get 1,300? Okay, so he's right. Had to happen sooner or later. All right, now let's test the second critical point, that 50, 150. So I'm plugging these into my z function. 8 times, oops, got to stick to my color scheme here. 8 times 50 plus 4 times that new y coordinate is 150.
What?
You get it yet?
Yeah, I did it already.
Oh my gosh. Rockstar.
Must have numbers.
Good point. Aiden, what'd you get for this one? Perfect. That's what I got too. Equals 1,000. And then that last one, 8 times 100 plus 4 times 150. And if you multiply this, what do we get? Anyone else? 1,400? Yeah? 1,400 good? Equals 1,400. All right, that's all the calculations. Now we just need to finally use this information to answer the question. Do you remember what the question was even? All right, so this is a little bit different because it says how much of each should she print to minimize the cost. So in this situation, do we want the biggest number or the smallest number? We want the smallest, right? I don't want to have a lot of costs. I want to have a minimal cost. And so just looking at these numbers, 1,000 is the smallest amount. So this will meet all those constraints of the number of brochures and flyers that I need to print, but it won't cost me that much money, which is great because I'm a business. I don't want to spend a ton of money. I want to make it. So I want to minimize this cost. And so this is the number of brochures and flyers. And so I can just write, she should make 50 brochures and 150 flyers for a minimum cost of $1,000. Boop. Thank you very much. That is awesome. $1,000 to make 50 sheets of paper. Holy cow. Good call, everyone. Yeah, back in the original word problem, our units here, I forgot about that this is 4 cents to print and 8 cents to print. So these units, this is actually not. And so to get the dollars, we would put a decimal point. So it's 13 bucks, 10 bucks, or 14 bucks. Thank you. Good catch. That's awesome. Oh, wow. How you feeling? Yes, this is pretty awesome. It's a long process. It is not a difficult process, all right? So I need you to get that mindset. These aren't difficult. There's just a lot of steps to them. And the best way to get familiar with them is just by doing some more of them. So I've gone through 2 of them with you. We've got 20 minutes left. I want you to try the next one on your own, okay? I'm going to be here to help you, to guide you. So here's the next problem. I'll make it bigger for you. And you have it in your packet there. And so I'll read this to you, but then I want you to go through those steps on your own. I want you to try to follow those steps to think about what we need to do to solve this problem. So Janet Smith wants to purchase at least 20 minutes of server time from this online company. And she needs at least 7 minutes from server A. The company will also rent server A only if the user also agrees to rent server B for at least 5 minutes. The rent for server A is $500 a minute, and the rent for server B is $200 per minute. And in order to minimize the total cost, how much server time should Janet purchase on each of those machines? So hopefully you can already see what your 2 variables are going to be for step number 1, X and Y. And then looking at that optimization word, you can see what you're trying to maximize or minimize. Use that to create your Z function. And after you do that, then go ahead and write your constraints. Ready, go.